Hey Calculus, Chapter 6 Review, number 1A. You are asked to take the derivative g prime of x of an integral, a derivative of an integral. That is your hint that you use the fundamental theorem of calculus, part 2. That is the shortcut. Okay? Your other hint is that your limit, one of your limits, has a variable in it. So when you see those things, the shortcut is you simply take that limit and you plug it in for the variable in your integrand. So it's going to look like this, the secant of x. That's it. That's all there is to it. Like I say, the biggest challenge is recognizing when to use it. All right, let's go over to 1b. Same thing here. Recognize we're asked to take the derivative g prime of x of an integral. One of our limits has a variable in it. So this is fundamental theorem of calculus part 2 again. The only difference here is that the variable is in the bottom. So the limits are flipped, and when the limits are flipped, you have to take the opposite sign of your answer. So again, we do the shortcut. All right, and there's two parts to the shortcut. The first thing you do is you plug in that limit in for the variable in your integrand. So it's going to be the cosecant, oops, thank you, typo, the cosecant of x cubed. Now, because this limit is not just x, we have to remember the second step. We multiply everything by the derivative of the limit, and the derivative of x cubed is 3x squared. And then again, because that limit is on the bottom, we have to take the opposite sign, so we put a negative out front. Negative 3x squared times the cosecant of x cubed. All right, let's go to number 2. Integrate. Integrate, if you remember, means find the antiderivative. All right, that means you find the antiderivative. So if you remember the antiderivative of 1 over x, that's our flashcard. It is ln absolute value of x, and this is an indefinite integral, so don't forget plus c. All right, 2b. Now we have a definite integral. So that is the fundamental theorem of calculus. So the first step is we find the antiderivative. So step 1, we find the antiderivative. All right, remember we call the antiderivative g of x. So in order to take the antiderivative of this function right here, let's rewrite it. Okay, we're going to go off to the side and we're going to pull it apart. And we're going to put 10 over 1 times 1 over x. If you multiply these two together, tops and bottoms, you get back to 10 over x. But now we have something that we know what to do with. That 10 is going to come along for the ride. And of course, we know the antiderivative of 1 over x. The antiderivative of 1 over x is ln absolute value of x. And then we use brackets to bring along our lower limit and our upper limit. So that's the first step, antiderivative, with the brackets on the end. The second step of the fundamental theorem of calculus, to solve a definite integral, we plug in our upper limit 3 into our antiderivative g of 3. We plug our lower limit 2 into the antiderivative, and then we subtract. So make sure you show these values. When I plug 3 into my upper limit, I have 10 ln absolute value of 3. And then I have, the second thing is 10 ln absolute value of 2, our lower limit. If we go to our calculator, when I plug in 3 here, 10 times ln absolute value of 3, we get 10.986. So 10.986. When I plug 2 into my antiderivative, I get 6.9315. Again, check this on your calculator. So our answer to our definite integral is 4.059, yes, 0.04, 4.0545 is what I am seeing on my calculator. So the answer to a definite integral is a number. That is the area underneath this curve, 10 over x, from 2 to 3. All right. Number 3, differentiate. What does differentiate mean? That means to find the derivative. So that means find the derivative. All right, so this is a composite function. You only see the letter x once, but there are 3 functions, cosine, e, and negative 3x. So this is going to be a chain rule, and since there are 3 functions, this is going to be a double chain. So let's write them out. The outermost function is the cosine, because we're taking the cosine of e to the negative 3x. So our outer function is cosine. Our inner function is always everything else, e to the negative 3x. Now we know that there's a second chain because we counted the functions, but we can also catch it right here. There's still 2 functions here. So now the outer function here is e. So in our second chain, the outer function is e to something, and then our inner function is negative 3x. And now we go to work. The derivative. All right, first chain, the derivative of the outer, the derivative of the cosine is negative sine, blank set of parentheses. Whenever you take the derivative of the outer, you always put in a blank set of parentheses. Right here is where we're going to plug in the inner as is. So that inner as is, e to the negative 3x is right there. Now after the first 2 steps on the first chain, now we start over and we go to our second chain. All 3 steps. The derivative of the outer, well, the derivative of e to something is just e to something. We plug in the inner as is right in there. So the inner as is negative 3x. And finally, we multiply everything by the derivative of the inner. You only do the last step of the chain rule on this last chain. So the derivative of negative 3x is negative 3. So times negative 3. Now, the only thing left to do, of course, is to simplify. And really, the only thing to simplify here is the sign. We have a negative here and a negative here. So that's going to give us a positive out front, positive 3. The coefficient goes in the front. So I'm going to put e to the negative 3x and then times the sine of e to the negative 3x. There you go, simplified version. Differentiate. All right. Again, half the battle is knowing what to do when. Let's go to number 4. Okay, well, we are asked to take the derivative right here, dy dx. That's a symbol for derivative. And we're asked to take the derivative of an integral. This right here is an integral. So whenever you're asked to take the derivative of an integral, that is fundamental theorem of calculus part 2. Otherwise known as your fave, the shortcut. Okay, so if you notice now, there are variables in both the upper limit and the lower limit. So we simply do the shortcut twice. All right, I'm just going to put that in there. So we start with the upper limit. So we do the upper limit shortcut. Okay, so the shortcut tells us we plug in that upper limit everywhere we see the variable in the integrand. So that gives us the sine of x squared. And the second step, of course, is to multiply everything by the derivative of that limit. The derivative of x squared is 2x. So I'm just going to put that out front, 2x. And then we do minus. And then we do the lower limit shortcut. We just do it again. All right, so the lower limit is e to the x, so I'm going to plug that right in here for the variable in my integrand. So that gives me the sine of e to the x. In the second step, I multiply everything by the derivative of that, which is just e to the x. And that goes out front right here, e to the x times sine of e to the x. So there we go. There is our fundamental theorem of calculus part 2. Nothing to simplify. Okay, let's keep moving along. We are going to review or go over L'Hopital's rule. Okay, so the first thing we want to do is make sure that L'Hopital rules applies. So we do direct substitution. We put this in. So when we put in 0 on top, 4 times the tangent of 3 times 0 does indeed give us 0. Make sure you're checking that on your calculator. Make sure you're in radians. And when we plug in 0 in the denominator, 5 times 0 is, of course, 0. So L'Hopital's rule does apply. All right, so the first thing we do is we take the derivatives. All right, derivatives. So the limit as x approaches 0 is still there. We take the derivative of the numerator. The derivative of the numerator up here, that is going to be a chain rule. All right, so the 4 comes along for the ride. The derivative of the outer function tangent, the derivative of the tangent is secant squared. So secant squared of something. The inner as is goes right there, 3x. And then, of course, the derivative of the inner times 3. That's the derivative of the numerator. The derivative of the denominator, the derivative of 5x, is just 5. Okay, so now I'm going to simplify that. When I simplify that, hey, the 4 times the 3 is going to give us a 12 out front. Oops, I meant to erase. So we're going to erase the 4 and the 3, and we are going to put a 12 out front. All right, now we go ahead and we do direct substitution. Oops, substitution. Okay, so when we plug in 0 right here, 12 times the secant squared of 3 times 0, we get 12 on top. And there's nothing to plug in on the bottom, so the 5 comes along for the ride. 12 over 5. So we have an answer. That is our answer. If we like the decimal, that gives us 2.4. And there is our limit. Now you can check these by looking at the graph. Graph this function and see if there's a good date at 0. See if the date is at 2.4. Okay, let's go to number 6. Again, do direct substitution. Plug in 0 on top. 1 minus the cosine of 0. Well, we know that the cosine of 0 is the x value, so that's 1. And 1 minus 1 gives us 0 on top. And of course, 0 in the denominator, 0 squared is 0. So 0 over 0 tells us that L'Hopital's rule does apply. So the first thing we do is we take the derivatives. All right, the limit comes down. The derivative on top, the derivative of 1 is just 0. Negative 1 comes along for the ride. So this is my numerator, negative. And then, of course, the derivative of the cosine is negative sine. So you need those both. Again, negative 1 comes along for the ride. The derivative of the cosine is negative sine of x. On the bottom, the derivative of x squared is simply 2x. Now, if we simplify that, we get the limit as x approaches 0 of positive sine of x over 2x. All right, and now we go ahead and do direct substitution. We plug in 0 for x, so direct sub. On top, we have the sine of 0. The sine of 0 is 0, and then 2 times 0 also gives us 0. So we still have 0 over 0. So what do? This is our hint that we do the derivatives again. All right, so let's keep going. All right, so we still have the limit as x approaches 0, but now we take the derivative of the sine of x. We know that the derivative of the sine of x is cosine of x. And then for the denominator, the derivative of 2x is just 2. Okay, so there is our derivative the second time through. Now we try it again. Direct substitution. All right, if I plug in 0 on top, the cosine of 0, of course, is equal to 1, and there's nothing to plug in on the bottom. The 2 comes along right here. So we have an answer now. Our answer is 1/2. Okay, let's go to the back side. Number 7, one more L'Hopital's. Now we're plugging in infinity. When you're plugging in infinity, you just have to think about plugging in a really big number. All right, a really big number. So I'm just going to write that out for you. You're just thinking about plugging in a really big number. So if we plug in a really big number on top, if we take 3, if we take a really big number and take it to the 5th times 3 plus 2, that still gives us a really big number. So we still have an infinity. And same thing on the bottom. If I take a really big number to the 5th times 7 minus 8, I still have a really big number. So we have infinity over infinity, and that is where L'Hopital's rule will help you. So we go ahead and we take the derivatives. All right, so we take the limit as x approaches infinity. The derivative on top is 15x to the 4th. 15x to the 4th. And the derivative of 2 is just 0. On the bottom, the derivative of 7x to the 5th becomes 35x to the 4th. And the derivative of negative 8 is 0. So you can see that still gives us, when we plug in infinity in for x, that is still going to give us infinity over infinity. So now we do the derivative again. All right, so now we take the derivative of the top. The derivative of 15x to the 4th is going to be 60x to the 3rd. 60x to the 3rd. And the derivative of the bottom, 35x to the 4th, is going to be 140x to the 3rd. Again, I still get infinity over infinity when I plug in infinity. I'm still applying this limit here. It still gives me infinity over infinity. So now we do the derivatives again. All right, so now the derivative of 60x to the 3rd gives me 180x squared. And for the denominator, the derivative of 140x to the 3rd is going to be 420x squared. Now again, when I plug in my limit, if I plug in a really big number here and a really big number here, I still have infinity over infinity. So we keep going. We get to do the derivative again. You just keep going as many times as it takes to get an answer. So the derivative on top, the derivative of 180x squared is going to be 360x. And the derivative on the bottom, the derivative of 420x squared is 840x. And guess what? When we apply that limit, right over here, that limit as x approaches 0, and I plug it in here, I still have infinity over infinity. Woof! Now we go again. All right, this is a fun example, huh? Okay, the derivative of 360x is just 360, and the derivative of 840x is just 840. We finally have an answer. That is our solution. If you like the decimal better, that is just fine. You can write that as 0.43. All right, so in this case, we had to take the derivative 1, 2, wait a minute, back up. We took the derivative here once, twice, 3 times, 4 times, 5 times to get an answer. How great is L'Hopital's rule? Okay, the last thing that we're going to talk about for our Chapter 6 test is logarithmic differentiation. So let's go through these examples. If you remember, the first thing that we do is we ln both sides. All right, so we go to work. We take the ln of the left, ln y, and we take the natural log ln of the right side, 3x to the x. The second step in log differentiation is you move any exponents to the front. Okay, and that's just a log property. So on the left, there's nothing to do. There's no exponents here, so that stays ln y. But on the right, this exponent here, x, becomes or goes in the front. So that gives us x times ln 3 times x. All right? Okay, the next step is now we finally take the derivatives. All right, so on the left right here, this is we have to use implicit differentiation. And that's going to be using the chain rule. So the derivative of ln, the derivative of the outer, of course, is 1 over something. The inner as is y, so we plug that in right here. And we multiply everything by the derivative of the inner. Well, the derivative of y, we just call it y prime. That's the right-hand side. On the left-hand side, this up here is going to be a product rule because we're multiplying two separate functions together. So our first function is x, and our second function is ln 3x. So let's do the product rule. If you remember the fun song, it's 1d2 plus 2d1. So the first function as is x. All right. For d2, that's going to be a chain rule. So the derivative of the outer, ln, of course, is 1 over something. The inner as is 3x. And the derivative of the inner is 3 over 1. So that whole thing here is d2. All right, now plus the second function as is, so ln 3x. That is the second function as is, and then we multiply everything by the derivative of the first function, and the derivative of x here is just 1. So there is our product rule. Now, we want to simplify. All right, so the next step is we are going to simplify the right side. Okay, so we're going to leave the left-hand side alone for a minute. 1 over y times y prime. On the right, if we simplify this right here, hey, this is the same as x over 1. You can see that these x's cancel and these 3's cancel. So this whole thing right here, everybody, that simplifies to 1. So we get 1 plus, and then right here, this is just ln 3x times 1. So 1 plus ln 3x. So that simplifies really nice. All right, now our goal, remember, is to get y prime by itself. So we want to get rid of this y. The easiest way to get rid of something in the denominator is just put that on top. So we're going to multiply both sides by y. All right, so now we multiply both sides by y. All right, so if we multiply this side up here by y over 1, and I multiply this side by y. So over here, these y's cancel, and I'm left with y prime, and that was my goal, to get y prime by itself. On the right, we have y times 1 plus ln of 3x, and then my last step is to plug in my original equation up there for y, and that's of course on the right side. All right, so let's do it. Y prime is equal to, for y, right here, we go ahead and we plug in this equation. Y is equal to 3x to the x. So that becomes 3x to the x, and then 1 plus ln 3x. And that is our final best log differentiated answer. All right, lots of fun. All right, one more to go. Right here. All right. I gave you a little hint here. A square root is the same as a fraction exponent to the 1/2. So the first thing we do is ln both sides. So we ln both sides. So on the left we have ln y, and on the right we have ln of that whole fraction, x squared times, and I'm going to write that as 4x plus 1 to the 1/2. So there was our first step. The second thing we're going to do is we're going to use log properties to get rid of this fraction. We don't want a fraction, so we can expand division with subtraction in the log world. All right, so that's our second step. We are going to expand division, that fraction, with subtraction. All right, so for this step, the left-hand side stays as is for now. And we are simply going to distribute, or not really distribute, but we're going to put that natural log right here. We're going to put it in front of the numerator. So we're going to get ln x squared, and then it's minus, and then we're going to put that log in front of the denominator. So that's going to give us ln 4x plus 1 to the 1/2. All right, the third step is now we can move those exponents. All right, so now we're going to move exponents to the front, and of course that's only on the right side. So again, that left side has to stay patient. ln y. All right, now this 2 goes in front, so that gives us 2 ln x minus, and this 1/2 goes in front right here. So 1/2 ln 4x plus 1. So there's that. Okay, now we're finally ready to take the derivatives. All right, and of course that's both sides. So on the left, this right here is going to be a chain rule, just like the last problem. And that has to be implicit differentiation. And then on the right side, it's just two separate derivatives, two separate terms. So on the left, we have the derivative of the outer is 1 over something. The inner as is y, and the derivative of the inner is y prime. All right, on the right now, the 2 comes along for the ride. And we know the derivative of ln x. The derivative of ln x is just 1 over x. All right, now I'm going to make 2 a fraction because this is a fraction. Now we keep going. The 1/2 comes down. To take the derivative of ln 4x plus 1, that is a chain rule. All right, so this is a chain rule. The outer is ln, and the inner is 4x plus 1. So the derivative of the outer is 1 over something. The inner as is goes right down there, 4x plus 1. And finally, we multiply everything by the derivative of the inner. The derivative of 4x is 4, and the derivative of 1 is 0. So that just gives us a 4 over 1. All right, at this point, we are going to simplify the right side. So we're going to simplify the right side. All right, so 1 over y times y prime sticks around. When we simplify the right side, this right here we can write as one fraction, 2 over x. And then we have minus. When we simplify here, this 4 and this 2 can simplify to a 2 on top. So if we multiply across the top, we get a 4. If we multiply across the bottom, we get 2 times 4x plus 1. So that simplifies to a 2 on top. So we have 2 over 4x plus 1. Alrighty? So again, this simplified to that. And when we multiply that together, we get this. Okay, now we're finally ready for our last couple steps here. All right, the next thing we do is we multiply both sides by y. So when we multiply the left side by y, this is going to go away and we're left with y prime. And then we have y out front times what's this whole thing here. So I'm going to put that in parentheses. 2 over x minus 2 over 4x plus 1. And then finally, we plug in the original equation for y. All right, so y prime is equal to, y was our big fraction up there. So we have x squared over the square root of 4x plus 1. And then we bring this whole guy down. And that gives us 2 over x minus 2 over 4x plus 1. And that is our final best answer. You do not need to go any further than that. All right, calculus, I hope this is coming along okay. Please keep in touch. I sure miss you guys. All right, take care.